Okay, to take the derivative of this tangent, the derivative of this vector curve, just take the derivative of each of the components. So it's f prime, g prime, and h prime, and it would give you the tangent vector. Now the tangent line to the curve is the line through the point that's parallel to this vector. Okay, I'm going to just go ahead and give you everything out of section 13.2, and then I'll do some examples, okay? Because nothing's really too difficult. All right, the unit tangent vector. The unit tangent vector is going to have a measurement of 1 or a magnitude of 1. To get the unit tangent vector, you just take r prime of t divided by the magnitude of r prime. And that just makes this tangent vector a unit vector. And this is a bold T. I guess I should put a hat above it. But this is a bold T in your book. It's called the unit tangent vector. All right, if you can take a first derivative, obviously you can take a second derivative. So the second derivative is just the derivative of the first derivative, just like it is with regular functions. And you also need to be aware of the differentiation rules on page 898. They are the same rules you had for functions. It's just extended into vector functions. Okay, but the derivative rules, the derivative of the sum is the sum of the derivatives, things like that. If you have a product, you have to use the product rule when you're doing derivatives of vector functions also. So just look at those rules. And if you can take a derivative, then you ought to be able to integrate. If you're going to integrate a vector function, you integrate piece by piece, and you get a vector. You get an IJK vector. If it's a in 3 dimensions, if it's an R3. Okay, I'm just going to look at number 3. Or if you're asked to find, actually they want us to sketch the graph of this curve, find the derivative, and then sketch the position vector, which is r of t, and a unit tangent. No, not the unit tangent, just the tangent vector for the given value. All right, if you're going to trace this out, this is in 2 dimensions, so we can do this by hand. It's like graphing a parametric curve. So if you were going to look at it and look at the graph, I will do this. If this is t, this is x, this is y. If I'm going to sketch the graph, I'm going to take some positive and negative numbers, so maybe -2, -1, 0, 1, and 2. And I'm going to do it just like parametric. I know I get a vector, but I'm going to plot points instead of, I'm going to plot the tip of the vector is what I'm going to do. So if I have -2 right here, that's -4. That's going to be 4 plus 1, which is 5. -1, that's -3. And that's 2. That would be -2 and 1. This is -1 and 2. And if that's 2, that's 0. And that's 5. And it keeps going. Let's see. Right, the point -4, 5 is right there. The point -3, 2. negative 2, 1, negative 1, 2, and 0, 5. So I've got a curve that's being traced out like so, and it's going in that direction. It's being traced out by the tips of the vectors, is what's happening. Now, they wanted me to graph the position vector r of t at t is negative 1. Well, I've already got the vector. This is the vector. The vector negative 3, 2. The position vector is from the origin, negative 3, 2, and it's going to be to that point right there. That's your position vector r of t that traced out each of those little points. Everyone was a vector, and it traced out the curve. All right, the other thing I have to do is just find the derivative. So the derivative of this, r prime of t, is the vector 1, 2t, and evaluated at 1, r prime of 1, r prime of 1 is the vector 1, 2. So the unit tangent vector, if you were going to sketch the graph, you would go to that point, to the tip, and then you would graph the vector 1, graph the vector positive 1, 2, except it's negative 1. No, it's not, sorry. I'm substituting. Graph the vector 1, 2, and something's not happening right with my picture here. Oh, because this is supposed to be negative 1. Why didn't y'all tell me it was negative 1? Yeah, I was too. T is negative 1. Duh. This is still 1, but this is negative 2. Sorry. You're confused. I'm confused. T is negative 1, if I could read my problem. This is still 1, but this is negative 2. I was not getting the tangent vector. So do the 1, negative 2. My unit tangent vector comes down like that. And it is tangent to the curve. Sorry for messing that up. Okay, taking derivatives, y'all would be good with that, right? For a unit tangent vector, maybe I should do a unit tangent vector. Maybe like number 17. It's just a formula, but if your function r of t is t squared minus 2t, 1 plus 3t, 1/3 t to the third plus 1/2 t squared. And I want the unit tangent vector at t is 2. All right, so looking back at your formula for unit tangent vector, you need the derivative and then you need the magnitude. So the derivative of this vector is 2t minus 2, 3, t squared plus t. And since I need it at a specific point, I'm going to go ahead and put 2 in here. I'm going to find r prime of 2, which is going to be 4 minus 2, which is 2. That's 3, and that's 4 plus 2, which looks like 6. So my unit tangent vector is this vector, 2, 3, 6, divided by the magnitude of this vector. And the magnitude of this vector is the square root of 4 plus 9 plus 36, 49, that looks like 7. So this looks like this is going to give me the unit tangent vector of 2/7 3/7 and 6/7. And that is the unit tangent vector. It's 497. Just follow the formula. Let's see. What about one where you have to find a parametric equations for the tangent line to the curve? Do I need to look at one like that perhaps? Yes. Maybe let's just look at number 29. Number 29. X is t, y is e to the negative t, and z is 2t minus t squared. I have a point 0, 1, 0. And I need to find parametric equations for the tangent line to this curve at this point. So the parametric equations of a line, you know you're going to have a vector, your direction vector. Here's your point. All you do to get your direction vector is to take your derivative. So find x prime, which is 1, y prime, the derivative of that is negative e to the negative t, and z prime is 2 minus 2t. So this gives you the vector 1, negative e to the negative t, and 2 minus 2t. This is your vector that's parallel to what you need. You just need to know what t is. Right, so how can you find t? Exactly. If I put 0 for x, then I get t is 0. Does that work in everything else? Yes, e to the 0 is 1, and that gives you 0. So it looks to me like t is 0. So that is going to give you the vector 1, negative 1, and 2. If I did my math right. So now the parametric equations, x equal to, remember you need the point, and this is multiplied times this times your parameter. So I'll just put 0 plus 1 times t, so you'll know what I did. Y is 1 minus 1 times t, and z is 0 plus 2t. So in more simplified forms, parametric equation, x is equal to t, y is equal to 1 minus t, and z is 2t. And these are the parametric equations for the tangent line to the curve. Do y'all see any math mistakes? All right, any questions about derivatives, tangent lines? All right, let's look at integration. Again, it's just as you would expect it to be. So if I were looking at number 35 and I want to integrate this vector function, it's the integral from 0 to 2 of t I minus t to the third j plus 3t to the fifth k dt. So by definition, all you do is integrate each part separately. So you're going to integrate from 0 to 2. You're going to integrate t, that part. That's going to be your I hat. Then you're going to integrate, I'll just put the negative sign. You're going to integrate from 0 to 2. You're going to integrate t to the third dt. That's your j. And then you are integrating from 0 to 2, your 3t to the fifth dt, and that is your k. So then just integrate like normal. Integral of t is what? T squared divided by 2, evaluated from 0 to 2. This one is going to be t to the 4th divided by 4, evaluated from 0 to 2. That's negative. And this one is going to be 3t to the 6th divided by 6, evaluated from 0 to 2. So this is going to be 4 over 2, which is 2. This one is 2 to the 4th power, 16, so negative 16 over 4. This one is 2 to the 6th power, so 64 times 3 over 6 maybe. So this would be 2i minus 4j plus whatever that is. Is that 32? Right, that goes into that 2 times, so that gives you 32 ij k. So you integrate a vector, you get a vector. Okay, that's an indefinite. Now on an indefinite integral, on an indefinite integral, if you are integrating, and let me just say I'm integrating, well, if it's indefinite, remember when you integrate, you get your function and you always have to have a plus c. The same is true with vectors. If you're integrating a vector, you're still going to get a plus c. Traditionally, we group all the constants together at the end, but if you are trying to go backwards, like a problem like number 41, where you're trying to find what the original function is, then you have to put a constant in each of the components. So let me show you what I mean with like 41. I'm looking for r of t, and here's what I'm given. I'm given r prime is, and I'm going to write it in component form. This is 2t, this is 3t squared, and this is the square root of t. I'm going to write that t to the 1/2. And I know r of 1 is the vector I plus j, which in component form is ijk. All right, you're given r prime and you need to find r. So if you want to find the original function, what you're doing is integrating this. So when you integrate r of t, the integral of 2t is 2t squared divided by 2. That's going to give you t squared plus a constant. I'm just going to call it a. Is everybody following what I'm doing without writing it down? Comma. All right, now I need to integrate this one. The integral of this is going to be 3t to the 3rd divided by 3, which is going to be t to the 3rd plus another constant, v. And the integral of this, 1/2 plus 1 is 3/2, so t to the 3/2 divided by 3/2 plus a constant c. So I integrated with respect to t. That's what I did. I put a constant in all of those places because I'm looking for my original function. Now, this is your given. You're given that when you do, I'll put 1 right here. That means you put 1 for all your values of t. You get the vector 1, 1, 0. That means this thing right here, t squared plus a, must equal to 1. But you know that t is 1. So 1 plus a is 1. That gives you a must be 0. So this number right here is a 0. I'm going to take this one t to the third plus b, and put it equal to this one. And again, t is 1. So that gives me 1 plus b is equal to 1, which again says b is 0. So this one is 0. This is 0. This is 0. For this one, when I put 1 in here, I'm going to get it equal to 0. So this is 2/3, 1 to the 3/2 plus c is equal to 0. That means c is negative 2/3. Therefore, your original function, your vector function, is the function t squared, t to the third, and then 2/3 t to the 3/2 minus 2/3. And that is my original function. Did y'all follow what I did? I treated it as 3 separate integrals, found each of the constants that went with each piece to get a very specific formula. Okay, y'all sure y'all got this? Are you positive? I want to be sure. All right, because 13.3 is more formulas. I'm doing these both today because really, it's all formulas. Now that we know how to do integrals and derivatives, we're going to use them to find, first of all, the length of a vector curve. The length of the vector curve is very similar to your arc length formula for a function. If you want to find the length of the curve, your vector curve, where r of t is as we've been using it, f of t, g of t, h of t, and t is going from a to b. Then you just take f prime squared plus g prime squared plus h prime squared. You take the square root of that and integrate it from a to b. And that gives you the length of the curve. An example for this one, I'll just pick an easy one. Maybe number 1. My vector curve is t. 3 cosine t, 3 sine t. And it's from -5 to +5. And they want the length of the curve. All right, this is f, this is g, this is h, so I need the derivative. The derivative of this is 1. The derivative of this is -3 sine t. The derivative of 3 sine is 3 cosine. So I'm going to have to square this, square this, square this. So that's 1 squared plus -3 sine t squared plus 3 cosine t squared. And I'm going to need the square root of that. That's going to simplify a whole lot. And I would prefer to simplify it before I put it in a calculator. This is 9 sine squared t plus 9 cosine squared of t. Okay, all I did is take the derivative, then I squared them and add them together. Right here, I can factor out the 9 from this and this, and I'm left with sine squared t plus cosine squared of t. Do you remember the trig identity for sine squared plus cosine squared? That is 1. So this gives me the square root of 1 plus 9, which is going to be the square root of 10. So all I have to integrate is from -5 to +5, my arc length, or my length of my vector curve, times the square root of 10 dt. And you integrate that, and that gives you your value. Can everybody get it from here? It's just like the arc length formula. It's very comparable to the arc length formula that we've already done. Okay, now, we've already talked about the unit tangent vector. So if your curve is traced out by the vector function, if it's smooth, that means the derivative is continuous and not equal to 0. We have the unit tangent vector, which gave us the direction of the curve. It was tangent. We had this formula back in 13.2. We have the unit tangent vector. And then we've got the vector that is normal to this one. It's called the unit normal vector. And it is this formula. It is the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector. And it indicates the direction the curve is changing. Okay, the book does examples, and they're a lot better at drawing it than I am. All right, if this is your curve, this one is the unit tangent vector. This is the unit normal vector. All right, this is a binormal vector, but I didn't ask you anything about that. Just unit tangent and unit normal, like this. And what it tells you is the direction the curve is changing. So this curve is changing that direction at that point. So, to find that, do I need to go through one where you're doing that? I do. Okay. How did I know y'all would say yes? Oh, what can I do? Let's see. Let's look at maybe number 20. That doesn't look too bad. Number 20. My vector function is t 1/2 t squared and t squared. They want unit tangent and unit normal. So I need r prime 1 t. I'll copy the front. Yes. And 2t. All right, so that's r prime. The magnitude of r prime is the square root of 1 plus t squared plus this one squared, which is 4t squared. So that is the square root of 1 plus 5t squared. So the unit tangent vector is this divided by this. So it's going to be 1 over the square root of 1 plus 5t squared. It's t over the square root of 1 plus 5t squared. And it's 2t over the square root of 1 plus 5t squared. That's your unit tangent vector. Now, I'm not real happy about this. Because guess what the unit normal vector is? It's the derivative of this divided by its magnitude. So now I have to take the derivative of each one of these. Okay. Let's see, what am I going to do? I think I would rewrite this one right here, scratch paper. I would write that as 1 plus 5t squared to the 1. Negative 1/2 is what I would do with that. I can see that. And the derivative of that is negative 1/2 plus squared times the derivative of the inside. Yep. You can see this is going to get very tedious, so I'm not real happy. So that would be negative 5t times 1 plus 5t squared to the negative 3/2. So that's the first one. It looked like a really innocent problem when I pulled it out, didn't it? Then I need to do the derivative of that one. And then once I have the derivative of that one, I've got the derivative of that. I can just multiply 2 times whatever I get for the derivative of this one. So, by hand or by calculator, I'm asking. It's, if you do quotient rule, if you leave it like this, you do quotient rule, but then you've got the chain rule inside there because you still have a radical. Or you can change it, bring this up and have product rule, but you still have a chain rule and a product rule. So do you want me to keep going? Yes or no?
We got the formula.
That's what I'm saying.
Yeah.
You got the formula, you know the idea, you're going to find you found the derivative of this one, you're going to find the derivative of this one. Then you're going to square this, square this, square this, add them together, take the square root of it. Put one over the other. And yes, it is ugly. Okay. I apologize for picking an ugly one. Okay. Now, the last thing I want you to be able to do is find the curvature. Now, the curvature of a curve, there are 3 formulas for the curvature. It just tells you how fast the curve is changing at a certain point. How fast is it? Does it get really squiggly? Is it flat? The curvature of a straight line is 0. It's not changing at all. That ought to make sense. But if you've got something else, how fast is that curve changing at a particular point? So this is the symbol for curvature. It is the magnitude of the unit tangent vector divided by the magnitude of r prime. That's one formula. Or it's the magnitude of the cross product of r prime cross with r double prime divided by r prime to the third. Or, if your curve is defined by y is equal to f of x, then it is this formula. The absolute value of f double prime divided by 1 plus f prime squared all to the 3/2. Use whichever formula you prefer. Let you write these down, then I'll work a couple of these. Right, and number 21, let me see, they say use theorem 10. I didn't even label these as theorem whatever. Theorem 10 is this one, right here. I don't care which formula you use, but 21 gives me r of t is ijk 0 t to the third t squared. They asked me to use Formula 10, and that suits me fine because all I have to do is find the first and second derivative, then do a cross product. So I would do that. First derivative of this is 0, 3t squared, 2t. The second derivative is 0, 6t, and 2. Then the cross product is 6t squared minus 12t squared minus j, 0 minus 0, plus k, 0 minus 0. So this gives me 6 minus 12, negative 6t squared I hat. So for the curvature, I need the magnitude of this. The magnitude of this is the square root of 36 t to the 4th, which is 6t squared. Divided by the first derivative to the third power, the magnitude of the first derivative, and then to the third power. Here's the first derivative, so I need the magnitude of that, 9t to the 4th plus 4t squared, the square root of that to the third power, so that is 9t to the 4th plus 4t squared, and I would just write it to the 3/2 power. If you don't like that, you can write it just like that. The square root of that to the third power. You cannot take the square root of 9 and the square root of 4. You cannot do that. That's illegal algebra. That plus sign kind of holds them together. Okay, the only thing you might could pull out is a t, but you don't have to do that. Again, this is just a formula. It's the curvature. Okay, do you need me to do one like 27 where the formula, the function is just in normal function notation? This is y is equal to x to the 4th. All you have to do is use this formula now, because you've got y is equal to f of x, so you would just use this formula. Okay, take the second derivative and put first derivative and plug and chug. Okay, so do I need to do that? No. Okay, that is it for 14.2 and 14.3.